Okay, temperatures and black bodies. So a black body is something that emits radiation thermally. That is different than non-thermal emission. So if you emit radiation thermally, it just means that you're warm. So you are a black body. So are the heating elements in your toaster. So the next time you go and toast something, watch. They go from being just completely black and cold to eventually warming up so that they are a dark red and then a brighter red and then a brighter orange. And then if you're really broiling it, it might turn yellow. That's a black body. We can approximate stars as black bodies. Stars are not really black bodies, but we can fake it, especially at the longest bands. Sometimes we can approximate dusty disks as additional black bodies. So if you have a ring of dust that's all at the same temperature, you get a black body from the star and you get a black body from the dust disk. Please do not assume that the words SED and black body are interchangeable. I don't know exactly why people make this particular error, but a black body is a single temperature thermal emitter. The SED is the shape of the spectral energy distribution. It's what we're observing from these sources. So a star without dust will look like a black body, but it's not the same thing as a black body. You can't say we're constructing a black body for this star. We're not. We're constructing an SED for a star. So the black bodies you might encounter in your textbook might look like the top two figures. So I've got intensity as a function of wavelength here. Here they've labeled it power radiated at each wavelength as a function of wavelength. But in both cases they have this shape where as the intensity increases as the peak gets bluer in both cases. When we plot it, the plots here are not particularly specified. Here they're explicitly linear, but it's not specified on the y-axis. But when we make a plot, it's going to be log-log. So log spectral energy, log wavelength. And it's going to have this distinctive shape. And this is called the Wien side because in the 1800s, when they were trying to figure out what this shape was, somebody by the name of Wien was working from the blue end and was trying to mathematically describe the emission on that side. And then two different people, Rayleigh and Jeans, were both working on the long wavelength side, trying to understand that. And so that's the Rayleigh-Jeans side of a black body curve. So technically, both of the equations there, they look pretty hideous, but both of them define a black body. The one on the left is a function of wavelength. The one on the right is a function of frequency. So the other terms that are in here, K is the Boltzmann constant, H is the Planck constant, C is the speed of light, nu is the frequency of light, lambda is the wavelength of light, and T is the temperature of the emitting object. And of course, E is the 2.718 mathematical constant. So you can see that it's pretty complicated, but when you plot these in log-log space, it looks like that shape. And that will become familiar if it's not familiar already. Note that this really is a function of wavelength and that really is a function of temperature, and it's not just a matter of plugging in lambda nu equals C because there's calculus involved here. So here I have a movie of SEDs. So there's lots and lots of really important things embedded in this movie. So let's try to dissect what we're looking at. The y-axis is lambda f lambda, so it's a spectral energy distribution. And the x-axis is wavelength. It's log-log, and so it's got that distinctive black body shape. I have plugged in an array of temperatures and calculated the black body curve. The temperatures that I'm using are listed in the upper right, and then it's got a spectral type underneath, because the temperatures that I picked are the effective temperatures for the spectral type listed underneath there in the upper right. So the first thing to notice is that as the temperature increases, the peak moves left and the whole thing gets brighter. So that's important. The whole thing gets brighter and the peak moves bluer. The other important things to note in this movie is that I've got some vertical lines here. These vertical lines are denoting wavelengths of various filters. So the optical filters are all in here. I think the two vertical lines there are B and V, Johnson B and Johnson V. And then I've got some other wavelength filters marked in there. Then the two mass filters don't have any vertical lines. Then the IRAC filters have 3 vertical lines for IRAC 1, 2, and 3. And then maybe it's IRAC 1, IRAC 3, and IRAC 4. And then WISE is here at 12 microns, MIPS is at 24. It gets a vertical line. And then we've got 70 microns, 160, 250, and 500, which are some of the 160, 250, and 500 are Herschel bands. So you can see that the B and V filters are crossing that blackbody curve here when this is an M8, so it's a relatively cool source. Because it's on the Veen side of the curve, the source is brighter at brighter at V than it is at B. But watch those 2 lines as this movie happens. The slope of that line as it goes through those 2 filters changes a lot. Here it's positive, there it's flat, and now it's a negative slope. This is why B minus V so easily converts to temperature, stellar temperature. It's because the B and V magnitudes, the B and V wavelengths, rather, cross that blackbody curve as it's changing rapidly as a function of temperature for the characteristic temperatures exhibited by stars. So that's why B and V maps so easily to temperature. Now, the near-infrared only really encounters the peak, so the J, H, and K that's there. Let me get it sound so one of the M stars and let it stop there. Okay, so stop! The J, H, and K here only really leave the Rayleigh-Jeans side for some of the latest M stars. And then everything basically IRAC 1 and longer, the slope never changes. For hotter stars, it gets brighter, but the ratio doesn't change because the slope doesn't change. So the fact that that slope, that Rayleigh-Jeans slope, doesn't change through all of those temperatures means that the IR colors are 0 for anything that looks like a blackbody. In other words, stars without dust. The infrared colors are not 0 for things that don't have this SED shape. So if all we had were IRAC points, we'd be kind of stuck because we would only be sampling the Rayleigh-Jeans side of the curve. Fortunately, we have a lot of optical data for our project, so we can sample both the Veen and the Rayleigh-Jeans side, and then we have a much better shot at understanding what it is that we're looking at, knowing, for example, that it's a star and not a galaxy. Reddening is another complication, which we'll get to in a bit. So, the next slide here. If you've ever wondered why your textbook refers to effective temperature, this is why. It's because we're approximating stars as blackbodies. They're not, but they're close. So the effective temperature is the temperature of the blackbody that approximates the stellar emission. That's why it's effective temperature. So now, what about reddening? So it's the same physics as if you have a lot of dust in the atmosphere or a lot of pollution, maybe like from Mount Pinatubo many years ago now, it kicked up a bunch of dust in the atmosphere. And so for several months after that, we had gorgeous red sunsets because of all the dust in the atmosphere. So it's the same physics. The stars, the light that we're seeing from the stars gets scattered. So the stuff that's in our atmosphere makes the sunsets red. The stuff that's in the interstellar medium makes the light red. It's the same physics. It's scattering the blue light preferentially. So the movie that I have here, now before I was varying the temperature of the blackbody, now I'm holding the temperature constant. I'm holding it at a 5800 Kelvin blackbody. But what I'm changing is the amount of dust between us and this G2 star at 5800 Kelvin. The blue is affected much more than the red. The blue side gets pulled down very fast. I do not need very much reddening at all to affect the blue. Here in the upper right, we've got AJ because that's the units that my code works in. It's the amount of extinction at the J band in units of magnitudes. But some astronomers find it easier to think about AV. So AV is the amount of extinction in the V band. So you can see that AV gets larger faster than AJ. That's because V is shorter wavelength than J. And you can see when you watch the movie that the blue band, the blue side, gets pulled down really, really fast. It does not take very much dust at all to pull down the blue side. But then when you get into higher and higher magnitudes of extinction, then you start to affect the stuff in the infrared. That bite that's taken out at 10 microns is not a signature of a dust hole in this context. It is actually a big, broad absorption line from silicate absorption at 10 microns. So when I crank up the extinction, when I crank up the extinction really high, when I crank up the extinction really high, let me see if it'll let me do it. Yeah, right here. So that's actually an absorption line at 10 microns, but it's a lot. It's like 87 magnitudes at V band, which is about 15 magnitudes at J band. So it's a huge amount of extinction. So that's really just a really deep absorption line. So if all you have is photometry, especially if all you have is an SED that looks like that, you can't tell if this is a low mass star with no reddening or a high mass star with lots of reddening. So that extinction is going to affect the position of objects in color magnitude diagrams and color-color diagrams as well. So the main takeaway points, honestly, are all encompassed in this video. The whole idea, all of it, is encompassed in this video. So the next topic we're going to hit are SEDs and color-color and color magnitude diagrams. So just as a setup for that, I sort of see SEDs and color-color and color magnitude diagrams are sort of two facets of a giant metaphorical data cube floating in front of me. An SED allows me to see many wavelength points, but for just one object at a time. A color-color or color magnitude diagram allows me to see many objects, but just 2 to 4 wavelengths at a time. Both ways of looking at the information are very useful, and they're in entirely different units, but we're going to use them both. The points that end up being outliers in the SED will also make that object an outlier in the color magnitude diagram, and points that are missing from the SED means that the object is going to be missing from that corresponding color magnitude diagram.